All right, AP 9.6, the last section in the chapter. We're going to talk about multiple bonds. Shout outs to my next people that did amazing on Chapter 8 exam. We have Joel, Monique, Alice, Ingrid, Joshua, and Emily. Beyond impressive on your skills for Chapter 8. 9.6 is a very complex topic, but the cool part is in AP, you don't have to explain it. You just have to figure out how many you see of called sigma and pi bonds. So it makes it very, very easy when you don't have to explain it. So we're going to go the Rodriguez Cliff Notes version. So let's start at the beginning. So number one, in a covalent bond, oops, there you go, just making sure it's still there. In a covalent bond, we have seen so far that electron density has been concentrated symmetrically about the inner nuclear axis. So we're talking about that the majority of the electrons are concentrated towards the center of the atoms. We have two types of shape bonds. Okay, so we've already talked about S's and p orbitals. But we also have different type of bonds called sigmas and pi's. Okay, so let's start right there, sigmas and pi's. Sigma bonds, and the symbol for a sigma looks like a long stem O. Okay, it looks just like that. A covalent bond in which the electron density is concentrated in between two atoms. Okay, so there you go, pretty simple enough. All single bonds are sigmas. Sounds pretty easy to figure out, okay? And it is easy to figure out how many sigmas and pi's you have, and that's all you need to be able to figure out for the AP exam. When you chemists out there decide to study OChem or biochem or any of those, then you actually have to learn why it does this. So what happens is this: when you have an s orbital and an s orbital that come together, will they blend the orbitals together and you get this giant oval type of shape orbital, and it's called a sigma bond, and that's what it is. What about overlap if you have multiple bonds? Okay, so with a single bond, you got to think of it, it's that initial connection between the atoms. It's like that glue that keeps the atoms together. That's the initial connection. But what makes the bond stronger are pi bonds. Okay, so doubles and triple bonds. So when you have multiple bonds, so they're called pi bonds. And just like when you go to math class, how to write a pi, okay, nothing hard about it. Two lines, squiggly on top. A covalent bond in which the electron density is concentrated above and below the inner nuclear axis. Think of it as, now that you've made the connection between the atoms, what keeps the connection strong? So with a double bond, what happens is when you have your two atoms, whoever they may be, that first initial bond between them, that would be like your sigma bond. And then the other bond that makes it even stronger, that double bond, well, that bond is constituted as a pi bond. Okay, and what a pi bond is, it's just the shape of it. So if you have two p orbitals, because p orbitals are where double bonds occur, and when they come together, they're going to blend. But instead of like an oval shape like sigmas, they're going to have like this upper region and lower region type of shape bonds. Okay. For a triple bond, that initial connection between them is that sigma bond. But then the more bonds you share, obviously it's stronger, but these bonds are pi bonds. And ladies and gentlemen, I'm going to say it one more time. You don't have to explain to me why it's a sigma and why it's a pi. Can you look at a molecule and tell me how many sigmas you see and how many pi's you see? And that's the name of the game. Okay? AP makes it very simple when it comes to 9.5 and 6 about explaining hybridization and pi and sigmas. Don't need to explain. Just tell me what it is. Okay? So let's do some examples. So right here, I put in your notes, if I had like a diatomic hydrogen, that initial connection between them, well, that's the sigma bond. You always have to have a sigma bond. But the more you have, then you have pi bonds. So in that region right there between carbon and carbon, The initial connection is a sigma, and then the other connection between the carbon and carbon is a pi. But what about these bonds over here with the C's and H's? Well, those connections between the C and H's, those are also sigmas, and sigmas, and sigmas, and sigmas. So in this one molecule, I have 5 sigma bonds and 1 pi. Okay? Doesn't seem too hard to figure out. Right here between diatomic nitrogen, well, the first connection has to be that sigma bond, and then the other 2 bonds are pi's. So ladies and gentlemen, when you're looking at a region between them, you can only ever have in one region only 1 sigma, but you can have more than 1 pi bond in between it. So if you're going to add pi bonds, well, then you can add pi bonds. And when I label it sigma and pi, ladies and gentlemen, it doesn't mean that the bottom bond is a sigma and the other 2 top are pi, like this one right here with the X and Y. I could have labeled it any which way it is, but the point is you're not going to have to label it. You just need to tell me what bond that is. Is it sigma or is it a pi? How many sigmas do you have? How many pi's do you have? And that literally is the lecture. So let's practice this. Let's say I had ethylene, which is C2H4, and if this is the picture of it, and I drew it, I took it from the simulation, I built it and drew it. How many total sigma bonds and pi bonds do you have? Well, right here, this is carbon, that's carbon, and then your hydrogens. Okay, so we're doing review. This is the type of stuff you would see on the test. Okay, just you know how Rodriguez rules and A, B, C, double Z. So first, how many total sigmas and pi's do you see? Well, every initial bond between an atom, those are called sigmas. Because remember, it's the initial connection between them. So all of these are sigma bonds. Well, between a carbon and carbon, they have to have an initial connection between them. So one of them has to be a sigma. The other one is a pi. So you have 5 sigma bonds and 1 pi bond. What would be the hybridization around each carbon? Because remember, hybridization, we only look at the central atom. Problem is we have 2 central atoms. We have this carbon right here, and I don't think it's going to let me highlight that structure. Nope, it's not going to like it. So with this carbon right here, let me do it in a different color. We'll go pink. I have this region, I have this region, and I have this region. So this carbon right here has 3 electron regions. And every carbon, remember carbon has its valence electrons in the S and the P, and hydrogen has its valence electrons in the S's. Okay? So regardless, don't need to explain it. What would be the hybridization? So you have an S1, P2, because 1 plus 2 has to equal 3. So we call it an sp2. So the hybridization right here is sp2. Well, it makes it really nice over here also. I have the same 1, 2, 3. I also have 3 regions of electrons on this side. So this carbon also would be sp2. So ladies and gentlemen, the more centers you have, the more you have to figure out its hybridization. And if you have lone pairs, they count also as a region. So around each carbon atom, they're both sp2 hybridizations. What would be the electron geometry name and the molecular geometry name? Well, right here I have carbon, 3 regions, and all those 3 regions are 3 bonds and 0 lone pairs. 3 bonds, no lone pairs, and each one had no lone pairs. They're both going to have the same name, called trigonal planar. Lone pairs would have changed the names. And if I would have asked you about bond angle, what would have been the bond angle for trigonal planar? Okay, remember a circle, divide by 3, so 120. Okay, that literally is how you're going to see it on the test. Okay, so no joke, just need to practice. So right here, How many total sigma and pi bonds does the molecule have? Okay, so here's my molecule right there. So if you need to label it to help you, right there, there's a sigma. Every initial connection, they're all sigmas. Okay, so I have that many sigma bonds. Now right there in that double bond region, I do have one of them that is a pi. So I have one pi bond, and I have 1, 2, 3, 4, 5, 6, 7, 8, and I have 8 sigma bonds. Okay. What would be the hybridization around each carbon? Okay. Well, if I erased all my little sigmas and pi's, so I have to look at each individual carbon. So this carbon right here, if I'm looking at it, it has 3 electron regions. This carbon has 1, 2, 3, also has 3 electron regions. But this carbon over here has 1 on top, bottom, to the right, but also to the left. He has 4 electron regions. So these first 2 will have the same hybridization called sp2, because 1 plus 2 is 3. But this last carbon has 4 regions, so it will be sp3. Okay? And what would be the molecular geometry names around each carbon? So if I just want the molecular geometry name, I'm looking for the true shape name. So these first 2, I don't see any lone pairs, and they both have 3 regions. So it's going to look just like this one on number 1. So I would say carbon, let's say 1 and 2, and I would probably label it on the test like 1, 2, 3, are trigonal, planar. But this third carbon over here, so carbon number 3, sorry, my phone is blowing up right now. Carbon number 3 got, that one's tetrahedral. Okay, so they would each also have different bond angles. So these 2 would be a bond angle of 120, but tetrahedral would be 109. Okay, that's how easy it is, ladies and gentlemen. Easy peasy. Like I said, don't have to explain. Life is good. How many total sigma and pi bonds do you have in the following? So this is formaldehyde. If you've ever heard of formaldehyde, it's usually the chemical they put in bodies when they are decomposing, when they have died. It's a preservative of the body. It's a very toxic type of chemicals, and they don't really use it too much anymore. But it has been used in those purposes. How many sigmas and pi's? So each one of these is a sigma, and that double bond is a pi. So I have 3 sigmas, 1 pi, and I only have 1 carbon. That's my central atom. And how many electron regions do I have? Well, I got 3 electron regions, and it's got to equal 3, so sp2. And just so you know, the S and the P, ladies and gentlemen, those are lowercase. Okay, so sp2. And what is the electron domain and molecular geometry name? They're going to be the same because carbon doesn't have lone pairs. And the same thing, trigonal planar. Kind of coincidence that almost all these examples have been trigonal planar. However, the next example will not be. Okay, so try it yourself, ladies and gentlemen, as you're doing this. See if you get it. Push pause and then push play to check your answer. Total sigmas and pi's. So each one of these are a sigma. But in that space between the carbon and nitrogen, I do have 2 pi's in there. So I have a total of 1, 2, 3, 4, 5 sigmas and 2 pi's. Okay, so the more pi's you have, the stronger the bonds. And what is the hybridization around each carbon? Well, this carbon has 4 regions, but this carbon only has 2 regions. Okay, so that first carbon, we'll call it C1. First carbon has 4 regions, so that would be sp3. But that second carbon, the second carbon, because it only has 2 electron regions, with only 2, it would be just sp. Okay, and the molecular geometry names. So with each one having no lone pairs, but they have different amounts of electrons. So that first carbon, with 4 regions, that would be tetrahedral. And that second carbon with only 2 regions, no lone pairs, that would be linear. And we already know linear would be 180 and tetrahedral would be 109. Okay? So ladies and gentlemen, that's literally how simple it is. Okay? So in conclusion, on the basis of examples we have seen, we can draw a few helpful conclusions for using hybrid orbitals to describe molecular structures. So every bonded pair can share 1 or more pairs of electrons. The lines we draw in Lewis structures represent 2 electrons, and we know that. In every bond, at least 1 pair of electrons is what's called localized. So it is only localized in that one space between the atoms and that sigma bond. Okay, so localized means it's in a fixed position. Okay. The appropriate set of hybrid orbitals used to form that sigma bond between an atom and its neighbors is determined by its geometry. It's always about that geometry. And electrons with the sigma bond are localized in the region between the 2 bonded atoms and do not make a significant contribution to the bonding between any others. That's why it's a fixed position. If you got 2 electrons between H and Cl, those 2 electrons are not moving because they're between H and Cl only. So like I said, that's what we mean by localized. They are in that fixed position. When atoms share more than 1 pair of electrons, 1 pair is used to form a sigma bond. The additional pairs are pi's. Okay, we got that. And the centers of the charge density of a pi bond line above and below the internuclear axis, which you saw the pictures from above. Delocalized molecules with 2 or more resident structures can have pi bonds that extend over more than 2 bonded atoms. And when you have these electrons that can move to different locations, the atoms aren't moving, but the electrons can move, aka lone pairs can move into bonds and bonds can move into lone pairs. That's what we call delocalized, when the electrons can move because of resident structures. Okay? Paramagnetism, dimagnetism, they are 2 vocab words that could pop up on the AP test. It's very unlikely, but in case they do, I did put them on here. So paramagnetism just means unpaired electrons, strong attraction between the magnetic field, and dimagnetism, no unpaired electrons, and they have very weak repulsive between the magnetic field. Usually with this topic, it's being talked about with energy. I just always keep those 2 definitions in there. I haven't seen those 2 definitions on the AP test in a long time, but doesn't mean it couldn't happen. So I just wanted to keep those 2 words in there just in case. Okay. Other than that, ladies and gentlemen, that is the show. So I want you to be able to practice. Okay. And you know you need practice on this one. So right here, this was the practice free response question that was in the video 2.1, 2.4. However, you need to watch the video, the answers at the beginning of the 2.5, 2.7. So in this graph, you have these 2, N2 and O2. So when you're looking at 2 different ones, first, what does the Lewis dot structure look like? Does one have more bonds than the other? Is one stronger than the other? Does one have a bigger radius than the other? So look at number of bonds and the radius, the atomic radius. Are they different? Why would the curves be one has a larger minimum versus the other one? But why does one have this line shifted forward? Number 2 shifted more forward than number 1. That must mean something. So I know you guys asked examples about this, and I did find you one in the video to practice. Okay. Another drawing that you saw on here, this one right here was from 2017, so it was a very recent one, the last couple of years. So this was the structure. You had to draw your bonds and lone pairs. The answers are at the beginning of the 3.1, 3.3. Okay, and remember on Teams, ladies and gentlemen, they're all right here under the College Board, and there's your videos. What was the approximate value between the CL-SS bond angle? That's in here. So when they want the CL-SS, They're looking, as soon as you draw it, they're looking at that angle. So whatever this atom is showing, does it have lone pairs? Because just because you draw it like it's linear doesn't mean it's linear. Okay, because if it has lone pairs, it's not linear. 2017 even hit us with a second drawing question, okay, which was nice because my students know how to draw Lewis structures, okay, and this one should look very familiar for you because it was the bonus question on the test. So let's see what you should have put, okay. 2018, you've seen this one also. Here was a structure right here. Based on the structure, what is the hybridization on the nitrogen? Think you guys can figure that out, okay? But be careful when you're doing this. Don't forget lone pairs, okay? And right here, sorry, I got forward. And at the beginning of the 3.4, 3.6, oh, I remember this torturous question. It was a very long question. So in here, you're going to learn about this thing called intermolecular forces, and this is the big guy that's coming in chapter 11. You want to hear about the explaining chapter? This is the explaining chapter. Okay, you thought chapter 7 explaining was torturous? Just wait till chapter 11. It's probably one of the most important topics of chemistry of all time, but it's very hard to understand if you can't draw. So if you can draw, you have a great understanding of what's about to come, okay? So they gave you 5 different molecules, and then you answered the questions about it. I know, ladies and gentlemen, you're going to hear stuff about dipole-dipole, and you're going to hear something about hydrogen bonding, and hear something about London dispersion forces. I kept this one in here because some of the questions have to do with hybridization. So these questions right here, A and B, this has to do with chapter 11, okay? So don't freak out. I always want you to have examples of past AP questions in your notes, okay? Other than that, ladies and gentlemen, that is all she wrote, and that is the end of the show. So don't forget to upload